and I will start to record the meeting. Okay?
Yeah. Okay. Hi everyone. So the time is for 2 hours, right?
Yes, yes.
Recording in progress.
Okay. Yeah. Hi everyone. Welcome to
Oh, okay, okay.
tutorial on how to use quantum circuits.
Wait, Naresh, wait. We have to set up the audio in a manner that your voice goes to the audience. Just a second.
Okay.
Is there? Okay. Hmm? There? Connect. Hmm? What? What? No, when he's speaking,
Yes, sir. We will take this letter. Directly they will to the amplifier and go to the record.
you cannot take from here? Because I will take my laptop behind. Ah. Can you do it from here?
Yes, sir. Yes.
I will do it.
Yes, sir. 2 minutes.
Hmm.
Hello.
Is it is it there? No, not yet. Huh? Ah. Naresh, can you say something?
Yes, yes. Hi everyone. Am I audible?
No. Just a second. No. No, but it's not going from here. Actually, I can hear it there. So this person, Naresh, he will be speaking here, and then we want the audio to go to there and everybody listen. You have to change it to allow. No, this you have to change, right? Allow. Huh? Oh, allowed. Maybe Zoom, the output is, where is the output here? Speakers. Huh? Okay, now try. Try. Yeah, it should work here. Naresh, can you hear? Okay, just a second still. So it's actually coming on this computer speaker. Yeah. Hi Naresh. Speak. It's still there. Okay, I know. I'll tell you what. I think you have to change it here. Same as. Headphones. Hello. Naresh. Hello.
Hello.
Now it's there. Naresh.
Yes, Rahul.
Okay, great, fantastic. Okay, so now we can mute this, right? Okay. No, he should be able to also hear. Just 1 minute. So, okay, so, all right, so now.
Rahul, can you give me permission to share the screen? Sharing permission.
This is off, right? Okay, all right. Naresh, can you hear? Naresh?
Hello.
Can you hear? Oh, he cannot hear. I think we have to start at least one. Maybe start that. Okay. Naresh, can you hear? Hello?
Hello. Am I audible, Rahul?
Yeah, you are audible, but we also want to make sure that you can hear the audience if they want to ask questions. 1 second. So, if we use the mic, please use mic to ask question. But I'm using the mic, but he cannot hear. So, what to do? Maybe I just start here. Try. Naresh, can you hear?
Hello. Yes, I can hear you.
Now you can hear me?
Yes.
Okay, great. So,
Rahul, can you give me permission to share the screen?
Pardon me? Yeah, I will do that. I will do that.
Sharing right, so that I can share my screen.
Yes. No, so that's why we can stop here. You see?
This is stop actually. This is output, right, sir? We are in the meeting, so that's the reason the output will be voice will be coming twice.
Why will it become twice?
Here the audience can hear it directly.
Because the voice is going. Yeah. There we go. This is great. So, all right. So, yeah, welcome back, everyone. Okay,
Rahul, I still can't share my screen.
Oh, you cannot? No, in my options, I'm allowing all participants to share. Naresh.
Hi, Rahul.
Yeah,
Yes.
in my options, I'm allowing all participants to share.
Okay. Why I can't still share?
You can't share still?
Yes.
Huh?
Yes, I still cannot share. Maybe I'll join once more.
Yeah, maybe you log in once more.
Yeah.
You can share, right?
Recording stopped.
So actually, we are online now, so your voice is voice chat.
Yeah, I know.
So can we share our mic?
Repetition.
Then my voice will get recorded here. Yeah. The output will come here. You guys are able to share? Huh? Cannot we try to bring
Yes, green is
Green just has to go on game.
Hello?
Okay.
Yes.
Naresh, you try. Other participants are able to share the screen.
Okay, let me try now.
Hmm.
I still am unable to share. Maybe let me give permission. Um, okay, I see. Yeah, I can share now. Okay.
You can
Hello?
share?
Yes, I think I can share now.
Okay, great. Yeah.
Yeah.
So maybe you want to start sharing or?
Yes, let me start sharing the entire screen. Right.
Recording in progress.
Okay, everyone. Yeah. So I guess we're all set. Yeah. So as I mentioned before, we are happy to have Naresh today. And he was a PhD student in our group, and there at NUS and for part of the conference. And then later he joined as a research fellow at NPT Research in California, USA. And now he's working with James Morgan Chase as a lead researcher in communication and photography in quantum loop. So he will be, happy to take this class today on Qiskit. Okay, and then one more thing. I think, okay, Naresh, we are at
Yes.
NIT Warangal.
Yes.
As you may be aware, Warangal is not far from Hyderabad. And Naresh is also originally from not far from Hyderabad. Where are you,
Yes.
Naresh?
I'm from Khammam, which is like very near to Warangal actually, where native Warangal is situated.
Oh, it's very near to Warangal. Okay, nice. So great. So Naresh, over to you. Yeah.
Yes.
You guys ask any questions? I think what we can also do, of course, you can ask in mic, or you can also just unmute yourself and ask. In which case, I think we also if they unmute and ask, then also it will be recorded. Yeah. Great.
Okay. Okay. Should I continue, Rahul? Hello.
Yes, Naresh. Yeah, over to you.
Hi everyone. Welcome to today's tutorial on how to use Qiskit to program quantum computers. So let us start with our good old Google. And so the starting place to get started on quantum computing program on IBM quantum computers is IBM Quantum. So let's just search. So here you see the IBM quantum computing, and you can go to sign into platform, and it will take you to quantum.ibm.com. This is the starting place for us to do whatever we want to do. So first, let me sign out so that that way we can know. Okay. So once you come to this quantum.ibm.com website, so here you'll be you can create an account with IBM Quantum. So that way you can start program with IBM Quantum. So there are like couple of ways that we can go about doing this. One is like one, we learn how to do quantum computing programming on cloud, and another is in the our local machine. So first I'll go over broadly over how we go about programming using Qiskit on cloud. So once we arrive in IBM Quantum website, which is this quantum.ibm.com, then here you can create an account with IBM Quantum. So as you can see, you have like various options, like you can create an account which is fairly straightforward with your email or password and so on. So I've already created an account with IBM Quantum, so I'll try to log in. All of you can meanwhile maybe create an account if because it's a fairly straightforward process. Yeah. So once we create an account and log in, this is the dashboard.
Naresh, just hold on a second.
Yes.
So as Naresh is, telling to do various things, you guys do it. If you need more time, just request more time.
Yes.
Okay. All right.
Yeah.
So Naresh, we can do it a bit slowly, or because we have 2 hours today.
Yes.
So
Yes.
we can do it a bit. Yeah.
Yeah.
So just if you are having any difficulty, also you just raise hand and say. Okay. So now he's asking to first create the account in IBM Cloud. Okay.
Yes.
So are you guys able to do that? If anybody is not able to do that, please raise hand.
Let me go over once more, just to be on safe side. So we go to Google, we search IBM Quantum, and the first link, which is IBM Quantum Computing, we just go there, and then you see on the top right corner, sign into platform, and that will take you to quantum.ibm.com, which is where I'm asking to create an account. Are everyone able to create an account?
Yes, everybody is able to create the account now. Anybody are you having any difficulty? Still doing? Okay, Naresh, just wait a couple of like a minute, couple of minutes.
Okay, Naresh, we can proceed.
Yes. Okay. So once everyone is able to create an account, I think the page that we land in, once we sign in, is this page, the dashboard. I'll quickly go over what each section mean in this dashboard. So as you can see, everyone once they log in, they should be on something they call open plan. So on open plan, you will have access to certain quantum computers. So let's try to see what they are. And also you can, on open plan, you will have like 10 minutes of quantum computing resources per month. So 10 minutes is actually a lot. So the small circuits that we usually learn in classes and so on, so they usually typically take like few seconds at max. So as you can see, I used only 15 seconds of compute power in this month. And that is about the plan that each one of us will be in once we create an account, open plan. And you can of course upgrade to other plans, but as you can see, the pay as you go and so on, the other services which they provide, like depending on the expense. And that's about the plan. And the number of quantum computers that are available, as you can see, all QPUs. So here there are many quantum computers which are currently online, which are stated, like IBM Fez, IBM Torino, IBM Brisbane, and so on. These are all the computers that are available. And out of all these computers, this instance, the instances that are open to us, I think there are only 3 at this point, which is IBM Brisbane, Sherbrooke, and I think it's you. These 3 127 qubit quantum computers are available for use. Right. Let me go to dashboard again. So that is about the open plan and the quantum computers that we have access to. These 3 quantum computers are accessible. And in middle, you can see all the workloads that we submit to run on quantum computers are available in the middle. Till now, I have used like 282 circuits that I have ran on quantum computers, and one that I have ran like an hour before, and which is still pending. And on the towards the right side, they have sort of updates, and there is this in the bottom. There are like 2 things where documentation, which you can access. They have Qiskit is open source, like some part of Qiskit is open source, so they have really very well documented resources. And another is learning tab. Learning is one where we will actually use. That's where we can build quantum circuits on cloud. So let me first explore this documentation. Let me click. So as you can see, there are many documentations that are available, and things that there are. To be frank, I'll say that it's very well documented, very well. Whatever you need, you can just search online and you should be able to get. They also have a lot of tutorials that each of us can go through and learn on their website itself. So, right. So when you run these tutorials, like if you do take computing resources, use the quantum computing, I don't think it is counted in the 10 minutes. So that's one good thing when you actually learn, use their tutorials to learn. And that is about the documentation. And towards in the bottom, there's one more tab, which is learning tab. And once we click this learning tab, it will take us to learning.quantum.ibm.com, which is where actually we can build quantum circuits on online, on cloud. So let me first go over this learning.quantum.ibm.com website. And here, as you can see, they already have like some basic courses that one can start, like quantum computing in practice, and getting started with Qiskit, understanding quantum. They have some learning paths, everything. Now they have some courses which one can take, tutorials, many tutorials, and they have some lectures by John Waters, available on YouTube as well to cover fundamentals in quantum information and quantum computing. And they have various tools. One is this quantum composer, which we'll use to build quantum circuits. This is about this learning.quantum.ibm.com website. And now let's wait. How did we end up here? We first logged into our IBM quantum computing platform, and there we saw this in the bottom. They have learning tab. There's another way to go to learning thing. Like here on the top right corner, they have menu option where you can go to platform, documentation, learning, and so on, and other administration things. So let's first let's start with the learning tab now. So learning option will take us to this website where we can compose quantum circuits. Right. So I just clicked on composer, which is where we can actually build circuits. So this is something that I have built. So fairly simple process here. In this composer, as you can see, they have, let me first go over what each means in this website. So here in the middle, this is the interface where we will build our quantum circuits. You can add more qubits. Let's say you are trying to run a quantum circuit on, like, let's build a quantum circuit on 5 qubits. I can add 5 qubits. Let's say I want to delete, I can delete. So this is fairly simple process to add qubits and delete qubits. And on the left, you see there are many gates that are available for us. So that we can use to build quantum circuits. Fairly simple, like simple Hadamard gate. This is the control NOT gate. And this is swap gate. And this is S gate, and so on. And this is the measurement gate, control Z, and so on. So as you can see, we have access to many quantum building block gates like Hadamard and so on that we can use to build circuits. And
So Naresh,
yes.
Naresh, maybe can you just build one small circuit here?
Yes,
and
yes.
show-
Yes. I'm just going over the website first. I will build.
Yes. Yeah.
Right. And on the right side, you see something like as soon as I try to build something, this is getting updated, right? So what this is doing is on the right side, we see this is the Qiskit circuit. So Qiskit circuit, actually Qiskit programming, basically. This is a Python language. Qiskit is based on Python language. So most of the codes that we write are fairly intuitive, and as we go on, you yourself can note that it is fairly simple to catch up. If you have experience programming any language, like say C, C++, Java, and so on, you should be fairly able to quickly grasp what is going on in Qiskit at least. So Qiskit is a higher level language. And there's another thing, as you can see here, there is something called OpenQASM. OpenQASM is more like assembly language for quantum computers. So we'll be only coding in Qiskit, and as you build circuits, you can see Qiskit this being updated, and accordingly OpenQASM being updated as well. So this is about these 3 tabs, and in the bottom you see these probabilities. Like for example, as soon as we add like qubits, right? So these 3 qubits are initialized to get zeros. That's why you always see the 0, 0, 0 with probability 1. So this is saying, like, in computational basis, it is saying what state this qubits are in. And this Q sphere is the block sphere, as you can see. You can also have state vector and so on. And this is about this website. So here we have fairly, most of the things are clear. And here there is this file option where you can create new files, copy the file created, you can export the file once you create, and so on. And you can of course there's other fairly simple and intuitive options that one can see here. You can manage registers and so on. View theme panels, like what you need. You can customize this panel as well. Like for example, I've kept probabilities and block sphere. That's why they both are appearing for me. You can set whatever is more intuitive to you. And yeah, so this is about this website. Now let's go ahead and all of us try to let me just verify that everyone is here now on Composer page. And once everyone is here, so now let me first create a new file, right? And let me try to rename it workshop file 1. And this is the file name that I've created. And now let's first try to create EPR state. Very simple circuit, as everyone knows. First, we have to apply on first qubit Hadamard, followed by Control Z. This will give us, let me delete this extra qubits. Yes. So as you can see, like once I created this supposedly this should create us, you start in ket0, apply Hadamard followed by C0, you should get a state called superposition of 0, 0 and 1, 1, which is EPR state. So as you can see here, probabilities all 0, 0, 1, 1, it is saying it's half, right? And here, even here, you can see in block sphere 0, 0 and 1, 1. It's in superposition of 0, 0 and 1, 1.
Naresh,
Yes.
just 1 minute. Maybe I will explain it to them how this circuit is creating EPR. Just 1 minute.
Yes. Okay.
I mean, they're familiar by now, but let me just one more time tell them.
Okay.
Okay, you see the circuit he is drawing is like this. Ket 0, Ket 0. Okay, the circuit is always starting in Ket 0. Then Hadamard. Okay, what happens here? Huh? Then there is a Control C0. Okay, so 0 on Hadamard goes to, okay, let me say 0, 0 goes to, agreed? On Hadamard, Control C0, zero, zero, nothing happens. Control on 0, nothing happens. On 1, this flips. Agreed? This is our EPR state. Yes? Agreed? That is what he has done in the cascade. Okay?
Right.
Okay, Naresh, you can continue.
Yes. So as Rahul explained, the state that after the circuit that we built, the state on 2 qubits is EPR state, which is superposition of 0, 0 and 1, 1. So now let's try to measure this. So for measuring, you can see we want to measure in computational basis. So the tab is that this is the Control Z, this is the measurement that we need to do. So, and this is again fairly like a drag and drop thing. That all of us should be able to do this till here. All of you can explore like just dragging and dropping a few other qubits like, but yeah, please try to make this circuit and all of your
Try to make this circuit yourself. Huh?
Yes.
Try to make this circuit yourself. If you have any difficulty, you can ask. Okay?
Right.
So Naresh, let's give them a couple of minutes.
Yes.
Naresh? Naresh, can you hear? Hello? Oh, he cannot hear this mic. Strange. Huh? Naresh? No, oh, mute mic. Yeah, I muted mic. Oh, so I have to keep on. At least one has to be unmuted. Okay.
Okay.
No, it's
So
okay.
everyone is able to.
Unmuted all the time. Shall we?
Yes. So everyone is able to create this circuit. Yeah. Okay.
Yeah.
Yeah.
Yeah. Hi, Naresh.
Hello.
Can you hear? Naresh? Hello?
No, no, sir.
Hmm? Why? Why it is not working?
One second.
Microphone. Hello?
Yes.
Naresh, can you hear?
Yes. Yes. I can hear.
Okay, fantastic. So, yeah, I guess everybody is able to do that now. We can proceed.
Oh, okay. Perfect.
Okay.
So now that everyone has created this circuit, So now let's try to execute this on actual quantum computer. Before that, let's say you want to add few more gates and learn about gates. You can see here once you select one gate and then right click, you can see information about that gate that automatically pops up. And this is about this is to know what gates we are adding, what their action is, so on. And on the right, once we created this circuit, as you can see on the right, the code is there, right? Like it is saying, okay, from Qiskit you have this registers, classical quantum register, and then you created this fourth line is saying you create a quantum register of 2, and fifth line is saying you create a classical register of 2 bits, and sixth line is saying you call this a quantum circuit, like which composes of 2 quantum registers and 2 classical registers. And eighth line is saying circuit.h apply Hadamard on the 0th qubit. Ninth line is saying apply C control not on first 2 qubits, 0th and first. And as you can see, 10th line is saying you measure 0th qubit and note in 0th classical bit, and you measure first qubit and place the outcome in the first bit. So this is the circuit that we have built. So as you can see, this is fairly intuitive, right? And you can also see what is happening in the OpenChasm, the assembly language. Assembly language is much more simpler, but as the circuit gets complicated, it starts getting a bit more complicated. And,
so are many of you aware of the Python language? Huh? So you are able to see, follow it on Python also, that code? Okay.
Okay. So this is about the circuit that we created and the code corresponding to that circuit, right? So now let's go ahead and try to execute it on actual quantum computer. Okay. So as you can see on the right, there is a button, setup and run. So once I click that, then it shows up, it opens a window for me. Like let me show again, and this is a window. Here there are like 2 steps that we need to do before we can actually run. And first step is select the quantum computer on which we want to run, and that is the first step. And second step is we have options to some, let's say, tag and so on. We can add tags to remember the file that we have submitted. So as you can see, total this from the details of this quantum computer, there are like 110 pending jobs actually. There are like 110. So as you can see, the quantum computers are limited, and the people who want access to it is there are many people who are trying to access them. So currently there are like 110 quantum computers which are in queue to be run on IBM web quantum computer. Similarly, on IBM Brisbane there are like 133, and on IBM Shedbrook there are 487. So earlier they used to have quantum computers which are like very small length, like 10 qubit, 15 qubit and so on, but they have all been deprecated like recently, and they have given access to 127 qubits directly. And since there are only few that are available, so they are usually being very very heavy, like we need to wait for a while once we submit our circuit. So I typically pick the one which has least number of jobs. So in this case, the first option. And in the second step, the only thing that we can change is the shorts. Like shorts is saying that you run the same circuit to get the statistics right. Let's say you prepare EPR state and measure once, you either get 0, 0 or 1, 1 with probability half. But to get the statistics, you need to repeat it same procedure many times. So this shorts is what that is. So let's say what we are saying is, you run this prepare EPR state and measure 1024 times. That's what we mean by saying the shorts. So let's say typically there's 1000 or 1024, and let's say here it is EPR, and once I give some tag, this tag is optional according to what we want to label it, and then we can actually run on the quantum computer. That's it. And once I click submit, it shows this running option here on the right side, right? So it's like now it has once it ran, it said, oh, job sent to this this option is being coming on the second tab here. Okay, so right, so let me just go to composer again and let all of us, I'll give you once more. You click setup and run, and then select the quantum computer on which you want to run, and then you change the shorts. In case you want to change, you change, otherwise you just keep as is 1024, and you can of course give the tag that you want and then run on IBM, whatever the IBM that whatever the computer that you want to run on. You have 3 options, I believe, most of us, so you can pick what is available and click run. And since there is a lot of queue and so on, so let me go over my earlier submitted files, view all jobs. Okay, before that, all of you are able to actually run this circuit on actual quantum computer, like at least submit so that it is on the queue. Okay, perfect.
Yes, sir.
Okay.
Yeah,
So
yeah.
now-
They're able to do it, Naresh. Yeah.
Okay, so let me see, like for example, as you can see, there are like some circuits that I've actually ran. So let me go over them, like because now we need to wait 30, like for example, you can see here, this is the circuit that I have submitted. And you can see workshop file 1 sent from, and there is status, everything you can see, status, timeline, and so on. You can see it is saying estimated wait time 31 minutes. And actual power that actual compute we'll use is just 2.2 seconds. That's what is it's estimated. And status details is pending. So this is because we are in queue, of course, and we need to wait till it comes to our thing. And this is where you can see the circuits that we have submitted. So before going further, the circuit that we submitted is actually EPR preparation, right? But as you can see, once we come to the workload, once we submit, the circuit seems different, right? So this is because the reason is that so every quantum computer has architecture, like let's say qubit 0 and qubit 1, qubit 2, and so on. All of them are not connected together. Some of them are connected, and some quantum computers can implement Hadamard, some quantum computers cannot. So in this, the qubits that they can implement on the quantum computer that we submitted is that RZ circuit and square root X and so on. So basically, whatever the circuit that we want to run, they change that circuit according to quantum computer. And this process of changing circuits is called transpilation. So, but we don't have to worry about transpilation when we run circuits online. Like since we submitted our circuit online on cloud, so once we submitted, they actually changed the circuit according to the quantum computer, and then they will run this circuit and then give us the outcome. So if you do the analysis of the EPR state and the gates that they have implemented, it will be exactly the same. Just that instead of using Hadamard and so on, they use a different quantum gate set. So yeah, that is it. Like for example, in the classical case, like we can use and not gates and so on, and right, and not gate, or you can just use in I think it is NAND gate, and then implement any circuit. So it's similar to that. So every quantum computer has some gate set, and they will use those gate set to implement the quantum circuits. Right. So before now I hope everyone is able to submit the quantum circuit that we prepared. So let me go to some job that I have submitted and which actually ran, and we can see the statistics. So let me go to this one circuit. So which was actually, like, once it actually ran on the quantum computer, it shows the status changes to completed, and it says, like, for example, I submitted this quantum circuit yesterday at night 11, and it shows the time at which I submitted, the time at which it was pending, and time at which it ran. Like, for example, here you can see 2 seconds, and it completed in 11:27, in 20 minutes. And you can see I think I have run like a big circuit, so that's why this is a circuit like after transpilation and so on. This is the circuit that they ran. Okay, let me see if I have something, maybe EPR or something. Right, this is EPR state. So right, so yesterday I've run another this EPR state itself, like at 10 p.m. and it shows it ran for 4 seconds and so on, right? 4 seconds, and now this is this, and you can see chasm code, Qiskit, and I want to see what else, user statistics. Yeah, this is where you can see the statistics related to the job that we have submitted. Let me go to this learning. Okay, so let me see one more. This is the big one. Yeah, so this is the workloads page where we can see all the things that we have submitted actually. So let me go now to again the learning page. Right. And the composer. Right. So yeah, so this is it, like the way that we can actually run the circuits and see the things. I believe should be one more. I think once it is completed, we can see a bit more information on the circuits that we ran. See more details. Yeah, it is still showing it is pending. So I think we can come back to this once everything is done, once it is ran. So for now, like, let's say we can get back to composer, and this is more or less the workflow. Like, you come to composer, you build a circuit that you want, and then you run it on the quantum computers that are available to you, right? And once they are completed, you can see more details about the job that you have submitted and so on. So this is about running preparing circuits on cloud, and then running on the actual quantum computer. As you can see here, like in the bottom, you can also see the probability with which you saw the statistics. Like for example, for 1024 shots, you can see 51.95% of the time we got 00, and 48.04% of the time we got 11. So when we submitted the circuit, that this is the thing that it is saying, that 1024 times it came out to be thing, and this is this. I think this is done locally. but you can see this similar statistics once it is done on the quantum computer. Okay, so similar statistics can be seen once it is run on the quantum computer. So this is more or less that I wanted to cover about running quantum circuits online on cloud.
So
if
Naresh,
everyone,
this one was run on a simulator or actual computer?
this is done on simulator. This is not yet done on
Yes. Yeah.
actual quantum computer. The
Yeah.
one that we see, this is calculated or simulated
Yes. Yes.
on the local. Yeah.
Yeah.
This
So-
is still like, as you can see on the details, that it is still in under the queue. I'm sure everyone's is under the queue because they take it queue by queue. So it should be, everyone should take like 20 minutes for them to run this circuit now.
Okay. So you can see that, right? If in the EPR pair, if we measure, so he's measuring both the qubits. Okay. So if we measure, we should get 0, 0 with probability half and 1, 1 with probability half. So in the simulator, they are running it for, I don't know, 1, 0, 2, 4 times or something, right? And then
Yes.
exactly half the time they're getting 0, half the time they're getting 1. 0, 0, half the time they're getting 1, 1. Okay? When you run it on the quantum computer, it'll be near that, but little bit, it'll be away. You know, sometimes it might be a little bit more times 0, 0, little bit less times 1, 1. Something like that may happen. Okay? Okay.
So anyway, like once your circuit is run, you can actually go and check on the detail, check more details regarding this. So like now, should I continue with this, how to run this on local machine, Rahul? Like before that, let me ask, like if you have any questions related to this things, any of you please do ask so that.
Yeah, you have any questions? Yes.
So good morning, Naresh sir.
Yes, yes.
Okay, can design any one circuit. After run that program, can take one system that Brisbane.
Sorry, I couldn't hear you completely.
Yes, sir, yes, sir. So after run the program, then you can find out the readout error. So how to calculate that readout error, sir? After run the program, you can complete run the program on the system. When the job is done, we can take some another system. For example, to take the Brisbane system. So after completed that, how to identify that readout error. Readout errors. Yes, sir. Yes, sir.
Apparently, Naresh, for some people,
Yes.
they were already successful in running it on the Brisbane computer.
Oh, okay, okay.
And they are
I
getting
see.
the output, but it is showing something like readout error. So they are asking.
So not now, sir. Already previous my one circuit is there.
Previous.
No, previous.
Okay. So they ran it previously, and then they got
Okay.
something called as readout error.
Readout error.
And now you are asking what to do?
How to identify that?
How to identify readout error?
Yes.
No, are you getting the
Oh.
statistics?
Yes, sir.
Then you go with the statistics, right? Yeah. Do you know anything about readout error, Naresh?
I don't know, Rahul, but I mean, I'm sure that can be find out online. Like they have
You-
very good Slack channel. And
You want to
everything,
share? You
like-
want to share the screen? Maybe you can share the screen and show.
So as you can see, there is something related to IBM in quantum. As I said, right, like they have very well documented things.
Yeah.
So as you can see here, they already have said what is readout error and so on. Like
Yeah.
you can read about it in the API reference. You can see my screen, right?
Yeah.
I think this is
We can
what
see
you
the
are
screen.
trying
Yeah.
to ask, right?
Readout error. Ah.
Yes. So
But
if
the
you
main thing
understand
is,
then you can,
Yeah.
yeah.
So, but the thing is, main thing is, as Naresh showed, right? Once you run a circuit, you'll be able to see when you do a measurement, how many times they got some value, how many times they got other value, right? Then that will give you exactly the probability, right? That is the main thing. You know, you run the circuit, you get the output, you measure, you get the probability of the output, and that is what we are usually doing. Now, in your case, were you able to get this graph like how Naresh showed that one? Huh? Were you? No, maybe you share the screen. Huh? You share. Naresh, he will share the screen. Just a minute. Huh?
Okay.
No, you share the screen. Maybe I can allow multiple participants to share screen. I don't know. Okay, now I'm allowing multiple. Okay, okay. So he's saying that we can just continue. He'll ask later. Anybody else?
Okay.
Any questions? Huh? You have a question?
Should the number of classical registers that we initialize, mean the minimum number of classical bits in a classical register, be equal to the number of qubits that we initialize in the circuit, or should that be equal to the number of qubits that we measure?
There is no need, like you can actually have more qubits that registered, but they will all be like for example, I think you can also in this circuit, if you are asking like let's say I have more classical bits, it should still be fine. Just that as you can see here in the measurement statistics, right, you will have like instead of 4 you will have like 8,
Right.
because there are 8 possibilities for 3 classical
Right.
bits and so on. So I mean, there is no restriction that your number of classical bits have to be same, but we usually keep the number of classical bits to be the same as we need. So in this case, we needed only 2 classical bits. That's why I've kept only 2 classical bits.
Yes, but how do we understand that need? I mean, is that equal to the number of qubits that we have in the circuit, or is that equal to the number of qubits that we measure?
Sorry, can you repeat that?
Yes. So how do we define that need? I mean, you said we will initialize it as we need it, right? So should that be equal to the number of qubits in the circuit, or should that be equal to the number of qubits that we measure?
Typically, like number of qubits we measure, right? Like we would want the statistics. Let's say we measure like we prepare a circuit on like 10 qubits, but we measure only the first 2 qubits.
Right.
So measurement statistics, if we are taking only from the first 2 qubits, you can just create 2 classical bits and then store in those 2 classical bits.
Okay. Thank you.
Yeah.
And those classical qubits, it doesn't show separately classical bits, is it? When all will be overlapping or something, because as you create, you just see.
Okay, let's see, like, right? So here, let's say I have one more thing. So here, it still like seems to say that.
But
Hello?
yeah.
Yeah. Here it
It's
still
unmarked.
shows only the 2 qubits that I've measured.
Yeah, suppose we click on say C2, it asks for a plus, saying
Yes.
yeah. So if we click on that C2, we will see that plus sign. So if we add bit, uh, just not able to comprehend how this adding a bit, what role it is playing, because we see only the C3 if we add. So C2, C1, C, are they present and not visible, or it doesn't matter? Or?
They are present. Yes. Here, okay, I think they put like double gray line to indicate that there are many classical registers. I mean, like it is not like, as you can see, this the first qubit is going into, there is 0 here, right? So there, it means that 0th classical bit, it is being measured and stored in 0th classical bit. For the second measurement, you see 1 here. So it states that, oh, we are storing in the first classical bit, and so on. Like if I do the same on again on the third one, it will show on 2, right? You see here, it says that there are 3. Now let's say if I do one more, it will still say I measure again and store on the second only. There are only 3 classical bits, that's why. Let's say I have one more, 4. Now if I do the Control Z, let's say I create one more, and so now it shows 3.
Yeah.
Is that clear to you now?
Okay.
C4 means there are 4 bits actual, 4 classical bits.
Yeah. And that actually changes the way computational basis states is displayed, no? Below. Yeah, it does. Okay.
Right.
Yeah. Thank you.
Yeah. And also one thing that you note that let's say C3, there are 3, right? Then there are 8 possibilities. So in the bottom you can see 0, 0, 0 and 0, 1, 1. So the third bit is on the leftmost, first bit on the rightmost. So that is the notation that IBM follows. So 0th qubit is always on the rightmost, first qubit on the, and then you turn to the left. Start from the rightmost and then go on left, like that. So that's why that it is in 0, 0, 0 and 0, 1, 1 it is showing. Okay. Yeah. Any more questions?
Any more questions? Yes?
The dial after the measurement, right, is showing some values when we hover over the dial on the circuit, the right top dial. No, not here. On the circuit itself, at the end corner, there is some dials.
Just Naresh, just
Yes?
on the circuit itself,
Mm-hmm.
then there is on the right side, there is something, no?
This one.
Yes.
Oh, this one is, I think it is just that, I guess this is, let's see, I think this is some information on that qubit. Like you can see probability of purity of reduced state 1, let's see this one, probability of 1, 0, whatever. Yeah, I think what this is saying is following. Like once we measure, right, this is like for the one time, then it is in 0, 0 and 1, 1 state, right, superposition. Now you measure, it collapsed in 0 and 0. That's why you see probability of 1 is 0, probability of 1 is 0 in both. And in the Q sphere also you see only 0, 0. You don't see 0, 0 and 1, 1. You see only 0, 0. I think this is for one evaluation. Let's say you do it like multiple times, maybe sometimes it can show 1, 1 and things like that, depending on the last outcome, I guess. But yeah, but I think that is the case. Like on Q sphere also, as you can see, in the state vector also you see only there is only 0, 0, right? Let's do once more. Yeah. Actually, or maybe I do not completely know what this is trying to convey. Yeah, maybe we can search about it. I don't know what that is exactly, but that is my interpretation, the way I see. Like, it seems to say that like after we measure the state of the qubit, I think.
Sir, can I?
You want to explain, right? Huh? You want to explain? I used to explain.
Sir, those two are the classical bits after measurement. As they are in dark gray, means 0, 0. If you remove one measurement, sir, please remove any one of the measurement. Just delete both of them.
No, but it's still there.
No, sir. No, sir. It will come half the superposition state. If you apply a NOT gate on qubit 1, if we apply a NOT gate on qubit 1, it is going to be glow as 1. And those two quantum states are going to be as, one is in gray, another one is blue, which blue indicates the logic 1, means quantum state, classical state 1.
It's still there, no? That one is still there. Huh?
For the circuit what we have given, the output state is 0, 0. Thereby, the two classical measurement indicates the rightmost of the circuit displaying in the gray structure, gray color, which means 0, 0. If anything we have after measurement, if any state is having 1, that particular circle is going to be glowing sky blue, which means classical 1.
Right.
You can apply any input here, it will be blue. Initially input.
Okay, all right. Okay.
Yes,
But after the Hadamard, why is still like that? After the Hadamard, it's 0.
But initially you cannot apply any inputs again. Only initially it will be.
Okay, doesn't matter. Yeah, Naresh, we can proceed. Yeah.
Yeah. Okay. So I hope everyone is able to create this circuit, run, and this is fairly simple process, right? You come to IBM Quantum Learning and then come to Composer, build your circuit and then run, and then wait for it to run, wait for some time, and then after that you can go in the jobs and then check here in the Composer jobs. Here only you can see Composer jobs and you can check the status and about it and so on. So now this completes at least the first part, like where we actually run on the create circuits using graphical interface and run on cloud. So now let's try to do similar process but on local machine. So right, so let me go again to so for that, so the starting place is the following: Qiskit install. So install Qiskit documentation, as you can see. So very simple. You just search Qiskit install, and that will take you to install Qiskit documentation page. So here they have like a very nice way that for us to install Qiskit on local machines. So as you can see there, for Linux, for Windows and so on, they have given procedures. First your machine should have Python installed, and then you install something, and so there is a process that all of us can follow. But for my computer is Mac OS, so for Mac OS I can tell the procedure. For Windows also you can appropriately follow this procedure, but more importantly, like you can either follow this procedure or you can also just install one file that I'll say, and you can, from then I can tell how to go about installing. So you can see this video where he covers how to install Qiskit. So let me go over the process now. So there is this something called Anaconda. So this is a library file which has Python already in it. So you don't have to install Python again in your thing, in your local machine. So the reason why even Qiskit recommends installing Anaconda is the following. So Qiskit is a high-level language which uses libraries like NumPy, SciPy, Python, Matplotlib, and so on. So all of them different libraries are maintained by different organizations, and Anaconda ensures that there are no mismatches between all the current files, so that all of them can be run coherently. So that is why that they have stable versions of all softwares already installed. So, and it also gives a lot of flexibility to actually create an environment and then work inside the environment. Suppose something goes wrong, you can just delete that environment and nothing happens to your local machine. So because of those flexibilities, that even Qiskit recommends installing Anaconda. So let's say you just go to Google and then search. The first step is to search this Anaconda download, and then you just give your email, let's say this, and then submit, and you should get a download link for your email, and you can go to your email and just download it. So distributions are available. Distribution installation, they will provide a link for both Windows, Mac, and Linux. Depending on your machine, please install appropriately. Okay, so let me so Anaconda is already installed in my machine, so I can go over the process, but if all of us want to, I would suggest maybe first I go over the entire process, then after that each of you can do the process. Okay, so the process is the following. You first go to Anaconda download, just give your email address, they will send you the link to download, and then you download. Okay, once you download, it's a fairly simple installation process. You just double click the file that you downloaded, and then you should be able to install on the computer. Okay, now let me go to, once I installed Anaconda, then I go to open the terminal. So terminal is there for all the like terminal. I'm sure if everyone codes that, you should be aware of this terminal, from where you can give instructions to code and so on. So like, since I installed Anaconda, so it will already place me in some base environment called a base. So there is this environment base that they place me in. So by default, once you install Anaconda, and then you open terminal, you should be here. Depending on this ngbodu is my MacBook username, that's why it's there. And this is the base environment. So, and conda and list. This is the document, this is the command that one can use to list all the environments that I have created. Since I installed Anaconda, this is the base environment, and this is the additional environment that I've installed to learn Qiskit. So how do we go about activating this environment? So again, like, if no one knows, if you don't know anything about Anaconda, you just go to Anaconda environment, or just Anaconda environment, search about it, and here you should be able to know how to create environment, conda create, and so on. So conda info. So you have many options, like how to create environment, how to delete environment, how to activate environment, and so on. So there are many ways that you can create environment, and all of them are detailed in Anaconda website actually. So right now, let me go to terminal. Let me create another conda, yes, learn Qiskit. So this is the command that I have used, one can use in fact to create a new environment. Let's say I want to create an environment by name Qiskit. Let's say I call, or maybe workshop, right? Okay. So now this has created, you give Y, right? So now I have created a environment by name workshop. Now it is saying you use this command to activate it, right? Conda activate workshop, right? So now from base we have changed it to workshop, right? As you can see here, now we are in workshop environment. So what it means is like whatever I do from here on will be inside this environment. Let's say I mess up some distribution and so on, some installation issue, then you can always delete this environment, create a new environment and work in that environment. So this keeps like, this is like a tab sort of thing in that you can keep track of all workflows that you use to code. You can have maybe one environment to do your assignments, one environment to learn some programming language, one environment to do something and so on. Like here, I've used this workshop environment here to maybe show how to install Qiskit, right? So now once I'm inside this workshop environment, now let's say the first thing I would recommend do is you first install something called pip. Okay, Conda install pip. So what it does is pip is a file, is a library that helps us install further things inside this environment. So now let's say I want to install Qiskit. Pip install Qiskit is the command. If you don't follow what I'm installing, don't worry. I'll tell what to do first, what to do next, and so on. I'll go again the process. First, I install Qiskit. I want to install other things which are necessary. Jupyter notebook, pip install Jupyter. I will tell why I installed everything as well, why I installed, what I installed, and so on. And next I will install pip install matplotlib. This is for this we need for viewing nice graphical things when we run ports on local machines. And pip install I think visualization toolkit. Pip install. I can install pip install Qiskit Air. And I install pip install IBM runtime, Qiskit IBM runtime. Right. So most of the things that are necessary are installed now. So as you can see here, whatever I have installed, that they have given here, like for example, this is what I have done. First I have done is I have installed this Anaconda. This is what they have recommended. However, you can use Python distribution such as Anaconda. So this is the first step which I have done. I have installed Anaconda, and then second step is here they are saying environment, right? That's why I've created an environment by name workshop. And you can, this is one way to create an environment, but I've used the one that recommended by Anaconda to install the environment. And then I have installed pip. That is the second step. And then after installing pip, then I was installing whatever that are needed. Like for example, I have installed Jupyter, I have installed Qiskit, I have installed Qiskit IBM runtime. I need to install this visualization also. Okay. And let me install that visualization. I think for visualization they need this. Yes. Okay. Right. So what have done nothing out of the box. All I have done is like followed the instructions that they have provided in this install Qiskit website. The first step was installing Anaconda. They suggested to install Anaconda. That's why I have done that. The other way is you can also just install Python and then work also. That is another way. But I personally like Anaconda and create environment and work inside that environment. Then I created that minimal environment. I created an environment. Then I installed pip. Then I installed using pip. I installed all the things that they suggested me to install. Okay. So that is the process. The process should be the same for different machines. If your machine runs on Linux, you should follow the similar procedure. For Windows also the same procedure. Just that maybe commands might be different. Like for example, to create an environment on Windows might be different, or I'm not sure if it's different or not. Seems like it's still the same. Okay, so please follow the instructions depending on your OS, and yeah, and you should be able to at least reach here. Okay, so now once we reach here, now let me
Naresh, just one second. So are you guys able to do that, whatever Naresh told you till now? All this installation and all? Downloaded. Anaconda downloading is taking time. Okay.
Yes, I think it can take some time because I think the entire distribution is under 700 MB, I think, something like that.
Oh, 700
or you can also
MB.
consider installing Miniconda or something like that. Either thing should be fine.
No, so how do we do? We just proceed, or how do we do, Naresh?
Yeah, I think I would suggest I can proceed, and I first show how to code using the local machine, and the process, everything is there on online, and they can do that following that procedure.
Okay, all right.
And once I finish how to actually tell how to run on local machine, then I'll be there and they can actually do this procedure, and then if they find some issues, I'll be there to answer as well. Yeah. Okay. So let me go ahead and now since we installed Jupyter, so Jupyter is one thing that personally it's very helpful to code on local machine using something called Jupyter Notebook. So the flexibility that it gives is like you can have it's like you can go by block. You write something, you execute it, and then have some comments and then write and so on. So it gives some flexibility to as a coder. So I personally like Jupyter as well. I'm not sure if you used in your coursework, but let me open Jupyter Notebook and show how useful it is. Jupyter is also recommended by Qiskit actually to code. So now here, once I run this Jupyter Notebook command from terminal, it opens a browser. And here I can go to the file that I want to open. Let's say I go here, not this. Let's say hello world, right here. So this is it opens this. This is the Jupyter Notebook actually. Hello world is the file name, and you can of course create a new notebook and so on. You can save, download. Fairly intuitive commands that all of us should be able to understand from here. So since I opened, so one thing that I want to say is the following, that since I opened this Jupyter Notebook from terminal and where I have actually installed Qiskit, right? So like when I opened the Jupyter Notebook, so now as you can see here, it runs in Python 3, and it actually has everything installed. That it opens on the base of this Jupyter Notebook is the files that we have installed in that environment. So it has access to Qiskit, it has access to whatever that we have installed currently in that environment. So that is one good thing. So now as you can see, so the building block in the Jupyter Notebook is something called file, something called cell. So this cell is like is a markdown. There are like three parts: markdown, code, and raw. Like these are fairly again. You can see like headings can be in the markdown and so on. So you can see like markdown and come to this first cell, right? So here this turns again to code. So this is the cell where I want to code. And
Naresh,
let's say
Naresh,
yes.
I had a broad question. So can you hear me? Naresh, can you hear me?
Yes, I can hear you.
Yeah. No, so for example, you see these days, in order to do LaTeX, right? We can either install MicTech in our computer and do LaTeX or just do it on Overleaf, right?
Yes.
Now many people just prefer to do it on Overleaf, right? Because it saves them all
Yeah.
the installation and everything. Now in this case, do you see there are advantages to do it locally, or is still just doing it on the cloud is maybe easier?
Oh, I think like let's say I want to run build a circuit on let's say 120 qubits. I have access to 127 qubits, right? But as you can see in the graphical user interface, like it gets like difficult after let's say 10 qubits.
No, but can't you do Jupyter this coding, whatever it is, also on cloud?
Yeah, I think it should be doable on the cloud, but IBM as they don't provide environment or I think Google Colab does provide some environment where you can install diskette and you can also program. That is one way. I think there are ways that they are coming up. They are not like officially being used by everyone, but they such options are being opening up. Like I understand what you are saying, but I think they will soon be there. Like there'll be an environment that they will create, and then you can just log in and use that environment and code.
Yeah, because anyway, after the coding is done, the running execution will be on their machine anyway, right? Like either on a simulator or on an actual machine, it will be on IBM machine, right? So this is just to code essentially, right?
Yes.
So I'm saying that just to code, so they are providing this user interface with this drag and drop things, right? Gates and all that. But they're not allowing this interface where you can code in this thing, is it? Like
Yes.
this they are not
Currently
allowing.
they are providing. The people do it, or maybe at this point they are not providing like flexibility to code online on cloud. You can only you graphically build.
Okay, all right. Thank you.
Yeah. Right.
Just 1 minute.
So-
1 minute. There's a comment by a participant. 1 minute.
Okay, I was just trying Collab. Looks like it is working, like installing Qiskit.
In Collab. But a Collab, why you have to install Qiskit again? Huh? It's just invoking it, right? It's not install. Yeah, correct. So in Collab it is working? Okay, then if it's Collab is working, maybe you don't have to do locally. Up to you, but
Yeah. Like remember Rahul, last time we did on some person did it on Collab.
yes, that's true.
Yeah.
Yeah, one person did it on Collab. actually.
It does. Collab is another very nice way to do things online. So you can just install things on Collab. It also gives like cell wise, so you can in fact run some command, and then if it doesn't have that library, it also gives you can also install that library within that cell. I think so. It is also a nice way. I think.
Yeah.
But-
So yeah.
yeah.
So you guys can either do it locally on your computer, or you can try to do it on Collab. Either should be okay. Okay. Thank you.
But one good thing about doing things locally is like, once you install everything on local machine, then it is with you, right? So you can, it's just a one-time process.
No, that is
Then
true.
things-
No, Naresh, that is true. That is what I used to think about MicTech, it is with me. But for over the time, I am finding use of overleaf, even it is online, easier for some reason. I don't have to bother. It installs things on its own, and
Yeah.
even the editor is much more flexible, and there are a lot of things that overleaf allows for. So that's why
I think
yeah.
the good thing about this not migrating from local to online is because the collaborations, right? Like you want to share it with others, then you can't share your
No, not just collaboration. Not just collaboration. The editor is much nicer. It has a lot more. It can allow to do a lot more than what MicTeX allows. It has these options, right? Like continue with even if there are errors, and the compilation is much more. And it's not asking you each time there is a you do something to install and automatically all of that. Yeah, and then so the editor somehow is much nicer there. I mean, at least that's what I find personally. Okay.
Yeah, I agree.
Yeah.
I think like as this Qiskit becomes more mainstream, I think such things will come up. I'm already sure people must be using Collab as well.
Yeah, there for example, Overleaf has this option of auto compile, right? As you are editing, it compiles. Now I don't know whether that option is there in MicTeX.
Yeah.
Things like that.
Right.
Okay. Thank you.
Okay, let's continue. So here till now what I have done is first I have followed the procedure that they listed in the install Qiskit website, and then like once I created environment, install Qiskit and the other libraries that they suggested, then I opened the Jupyter notebook and I opened a file which I already created, and I'm just going over this code now. Like here you can see that I'm just invoking the libraries that I need, like Qiskit. I need this basically transpiler. I need to transpile the circuits according to the quantum computer that I want to run on, and Qiskit IBM runtime is needed for one is for transpiling, another is to actually use know what computers are online, what are active, and so on, and another is for visualization and so on. So these are the things that I just invoke now. Let me just run. Like I think it is busy now. That's why it is showing. It will take like, let's give it. Yes, it has. Once it has executed, so it shows here, right? So now let's say QC. So I'm just. This is a command like as we saw in the graphical user interface as well. Like you give like 2,2. The first argument is for number of qubits. Now second argument is for number of classical bits. And then now it's very simple that QC. Let's say we created a quantum circuit by name QC. The name can be up to us. You could have named anything, but I'll just call this QC. Okay, and QC.h. And .h is for applying Hadamard gate, and in the argument it takes like the number. Let's say you want to apply on the 0th qubit. So note that qubit numbering starts from 0, not from 1. So let's say you create 10 qubits, so there are like 0 to 9. Qubit 0, qubit 1, and so on. So here let's say I want to similarly prepare EPR state. So I want to apply Hadamard on 0th qubit, right? And I want to apply control knot on 0th qubit and then the first qubit, right? So now again I want to measure this 0, 1 qubits and update the measurement outcome in 0, 1 classical bits. So this command is simple, qc.measure, and then it takes in 2 arguments. The first argument is the qubit array, the number of qubits that you want to measure, and second argument is the array of classical bits where you want to store, and then you apply this. Now here is where you can see that qc.draw MPL. This is why we have installed matplotlib. So let's say you don't use matplotlib. I think it should be like see user interface is slightly not nice, right? So I think that just like matplotlib makes it slightly better. So people just use matplotlib. Yes. So this is the matplotlib output for the circuit that we have prepared. So this, as you can see, Q0, Q1, we have applied Hadamard here, fifth line, and then control not on 0, 1 qubits, and then measure, which is what you can see here, right? So now, right, important thing. So let's say this is the same circuit that we created in the graphical user interface, right? So now let's say I want to, now I have like two options. One, I want to run on actual quantum computer. Two, because actual quantum computer gives us only little compute power, I can actually simulate my quantum circuits and then see before I actually run on quantum computers. So that is why I have installed Qiskit Air when in one of the libraries. So that's why like Qiskit Air is a library where they have various powerful simulators. Okay, so Air simulator is one which is very nice. So we will be using that Air simulator. So again, this is not much necessary for transpiling for simulator, because simulator actually does use standard, but we will do anyway just to get clarity on the process. First you invoke simulator, and then you transpile your quantum circuit according to simulator structure. Simulator also will have some backend. Simulator is a backend, some actual quantum computer that you want to run, simulate, and then this is transpiled is the circuit that it will transpile. So remember that I have said that when we want to run circuit on actual quantum computers, then they will transpile the circuit to the quantum computer architecture and then run that transpiled circuit, right? So here on your local machine itself, you can transpile the circuit and then see. Since we are only doing it for simulators, so transpiled circuit will be the same as the original circuit. Simulators are more or less perfect, but one backlog of simulators is that, like, let's say you cannot run, like, let's say on like more than 50 qubits, you cannot hope to run quantum circuits. Okay, because of the like exponential law of the density matrix and so on, 2 power 50 dimensions. Because of that, it's hard to simulate beyond 40 to 50 qubits. Okay. So first, so now we have transpiled some circuit to the backend that we want, right? And the third step is like, let's say you want to run the circuit. So very simple. Here we have created the simulator. So we'll just, the command is simple, simulator.run. And then it takes as input the circuit that we want to run, which is QC transpiled in this case. And then I'm actually like running it for 1000 times. And then, and this gives us a dictionary. And then I just get a result from that dictionary and then output it. So this is a fairly simple command that one can use. And inside result, you will have some statistics that we have performed. Like remember that we said simulator to run 1000 times this EPR state preparation and followed by measurement. To do 1000 times and then get the measurement outcomes and then store it in result. Now inside result, it is stored in certain way. So the way to get this counts, number of times that we saw 0, 0, 1, 1, is like it just counts is an array now. Now you can plot histogram of counts. So as you can see, if you add 491 and 509, it is 1000, right? So basically it has done like for 1000 times, it has prepared EPR state and then it has measured 1000 times. And every time you do, with probability half, you will see 0, 0, and with probability half, you will see 1, 1. One good thing is you didn't see 0, 1 and 1, 0. You see, you saw only 0, 0 and 1, 1, but close to half. Like as you increase this 1000 to let's say 2000, you should see bit more closer than 491 like that. Let's see this. Now let's get this. Now let's try to run. Now here you see 973 and 1027. Like as you run more times, this starts approaching close, much more closer to half, and so on. Okay. This is about actually preparing circuit and running on simulator, right? Let's say now I want to run on actual quantum computer. So now this is where this Qiskit IBM runtime that we installed in the environment comes into play. And here it is very simple. Its code is very simple, that you just invoke this Qiskit runtime. So it has two inputs. One is IBM quantum and another is token. So this is where, one of the important things, that how do we tell quantum computer, that IBM website, that this is, let's say I'm invoking from this machine or from this account. So this token corresponds to the account that we want to run. So this is my token. So everyone can see their token in the IBM website. Let's say I go to IBM Quantum and sign in. Here you see API token, right? As soon as you log in, you can see API token. So you can just copy it, and then here you can just paste it, right? And then once you paste, and then you should be able to actually invoke using Qiskit IBM runtime, invoke their runtime service to get the details about available quantum computers online. So this backend service.leastbusy is a very good command that IBM provides to get the least busy service. So we don't want to run on like heavy most busy one. So typically it's helpful to get a backend which is least busy and run your circuit on the least busy one, right? And let me see, right? And now they have provided this pass managers are the ones which are like the transpilers. So basically this it takes as input the backend, like backend is the least. So basically the least busy quantum computer, I have invoked it in the local machine. So I have it now. So its name, and then this optimization level also. So there are like levels, like let's say you are invoking a big quantum circuit, let's say 127 qubit quantum computer and 127 qubits, and then let's say of the depth like 50. So then this preset pass manager will take a lot of time to transpile the circuit, and so that's why they have provided this optimization levels. So there are like 3 levels, I believe, and 3 will take lot of time. So I just put 1. So basically optimization, like how do you want to optimize, how to minimize the number of gates, how to minimize the number of depth of the circuit, transpile circuit, and so on. And okay, now once I get this pass manager, then I can just run and give this our quantum circuit QC as input, and then it will give us as output the transpile circuit. Okay, now let me draw this transpile circuit. You see, this is similar to the circuit that we saw like on the online, right? Like when we created graphical user interface, and then when we tried to see the circuit, submitted the circuit, the transpile circuit looked similar to it. So this is similar circuit that you can see. And now let's say I want to run this circuit. So what have we done till now? Let me just go through. First, we have invoked some libraries. We created the circuit. Circuit creation is very simple, like Hadamard, Control X, Measure, and so on. And then we have used how to use simulator to run this circuit for like 1000 and so on. Then we use the pass manager and the IBM runtime to transpile the circuit first to this. Now the next step is, once we have the transpile circuit, then we want to run this circuit right on the online. So for that they have provided this sampler, which is sampler v2, like version 2. So then it will only take as input like the circuit, the quantum computer that we want to invoke, and then the number of times that we want to invoke. Like you can name it 1024,000 and so on. And sampler.run, our transpile circuit, will do the job. Okay, and warning, the pending jobs limit has been okay. So I think this is one more thing. So at a time, because they want to control the number of jobs that people submit, at a time each person can have only 2 things in the pending. So only after 2 jobs are, like 2 quantum circuits that you want to run are finished, then you can submit one. So like for example, I have like 2 pending jobs here, as you can see here, like in fact 3. So that is why they have said that the pending jobs limit has been reached, waiting for job this to finish before submitting the next one. So basically you can use this code, and then you can also use this code to know the job ID. For example, this is a job ID that I submitted yesterday. So you can go and check here, and then it should be visible here. So that is the process, but let us see if anything finished here. Right, I think all the jobs currently that I submitted are still pending. Okay, so anyway, like once that's it. So once I execute this job is equal to sampler.run, then it will create a job and it will be in the queue. You can go and view in the website, actually in the job here in the workload, you can see all the jobs that we submit. So once we submit, then you can of course have this job is the basically once it runs, then once it is completed, then it will assign all the outcomes of the measurement, everything that we invoked, to this file, to this element variable called job. And then from there I can get the result. I can get the counts, number of times I see 0, 0, number of times I see 1, 1. Then I can basically plot the histogram of the counts. So that's why, like, which I have done yesterday actually. And then as you can see here, I've done 1000 times EPR state preparation, and I've run on the quantum computer. And then as you can see here, like 0, 0 and 1, 1 has occurred, 5, 1, 8, 4, 7, 3, and 0, 1 and 1, 0 also occurred. So this is because the actual current quantum computers are like prone to some minute errors. They don't exactly implement the quantum circuit, but they implement approximately. So that is why we see some errors here. But as you can see, when we did simulate, we didn't see any error, right? We didn't see 0, 1, 1, 0. We saw 0 and 1, 1 with approximately equal probabilities, right? So this is about thing, and I have plotted to compare with the statistic simulation and the experiment. And you can see this in the experiment, there are some errors, 0 and 1, 0. And in the simulation, you see perfectly that count of 0, 0 and 1, 1 sums up to 1. And there are no 0, 1 and 1, 0. And so on. So, right. So this is about like preparing quantum circuits in offline, and then also running them online, running them from your local machine using your account token and this code. So there is, I understand this can be a bit lot to grasp, so I will try to go again the entire procedure, but fastly, and see that I will also provide this file actually, so that you can once you install everything on your local machine, you can also open your Jupyter notebook and analyze this code, and then run cell by cell and understand what has happened from start to end. So let me just go over now. So we first created installed Anaconda here, and then we created an environment. Then we installed everything that is needed as suggested in the website. Then we opened our Jupyter notebook. Then we invoked this whatever the libraries that we need from Qiskit, created the circuit, then visualized this circuit. Then we actually ran on simulator to know the statistics of the circuit that we created. Then we wanted to run it on actual quantum computer. Then we use this Qiskit IBM runtime service, their library, to get the least busy quantum computer. Then we need to transpile the circuit. So we use the pass manager is a command that they provide to transpile the circuit. We transpiled the circuit, original circuit, to use the transpiled one. And then we use this command sampler to run our transpiled circuit on the quantum computer. And yeah, and that's it. Like because I already have 2 jobs submitted, so this is showing that I cannot submit again. But otherwise, yeah, like I think when all of you run this, it should be all of your jobs should be submitted and run, so it should be fairly okay. Yeah. So this is more or less I wanted to cover in running from local machines. So let me just.
Okay, so you guys were able to do these commands locally, or on that Google Colab or something like that, huh? Yeah. He's going to provide this Jupyter notebook. Yeah. This Jupyter notebook he will provide. Yes.
Yes, I will provide this Jupyter notebook. Yeah, like procedure. Let me just, like, you can see in this. There are many videos online. Like, in case you find this overwhelming, also there are many videos that are available online. Like, for example, here how to install Qiskit. Here in this video they provide for Mac OS. But I have found there are other videos available for Windows, Linux, and so on. How to install Qiskit 1.0. So when you install Qiskit 1.0, okay, this 0 point is deprecated now and they don't use. So you try to install latest version of Qiskit, which is 1 point something, 1.27 or something like that. Qiskit 1 point something. So when you install, it should be So there are many videos online in the YouTube as well, like if you want to install and so on. So in text, everything is here actually in this install Qiskit web page. Here you have for Mac OS, Linux, Windows, the procedure that I followed. And after that, then I went to the Jupyter notebook, and then I've given the commands how to install, how to prepare circuit, transpile circuit, run on get the least busy quantum computer, and then run on it. Right.
Okay, Naresh. So another thing is, we are slightly past 1. Usually we have class like 11 to 1, but we started a bit late because we were doing setup and everything. So how much time do you think you might need more?
This is more or less I wanted to convey, like at least tutorial wise, the both running on online and also like graphical user interface and running locally. Like
but you wanted to also run these example circuits, right? This 4-on-1 Grover and things like that, or?
Right. Like yeah, I do have everything. Like you wanted to give it as assignment, or should I actually run everything and then show them? You can
maybe we can run a few, because we ran one, right? But that was small, that creating EPR. But maybe we can run like maybe one of them at least, so that they get an idea, more idea of running a little bit bigger circuits. And then later we can also give something else for assignment. But I think it'll be good to give at least one more of that, right? Maybe a 1-on-4 Grover or superdense coding, whatever you are planning.
Yes.
Do one more, right? And And also, if possible, actually run it on the cloud, like on the actual quantum computer, and see the statistics. You know what I'm saying?
Yes, yes.
Yeah.
Right.
Is it like a lot on the queue? I mean, is it taking a lot of time?
I think currently it is taking a lot of time. You can see right here, it is still pending. Like there are like three things that during this tutorial I have run like 3 times, right? So all three are currently in pending. That's why it is not allowing me to submit another job.
And like, is it because we have chosen a certain machine, or is it like some other machine maybe more freer or anything like that, or?
I think it is like they have limit to number of circuits that one person can run on. Like at a time, I think only 2 or 3 circuits can be pending, I think.
No, that's fine. No. What I'm saying is that, is it pending because we are trying to run it on a certain server? If we change the server, it becomes. Is there another server which is freer or something like that, or is it is like automatically trying to optimize on which server it has to run?
Okay. When from local machine, I have tried to get the least busy one and then try to run on it, right?
Okay.
Even the least one is
Even
currently
the
pending.
least one is taking time. Okay. All right. So yeah. Okay. So if you want to do one more example, you think it might take another half an hour or something, right?
Right. Like I think I might need. Like I do have it ready. I can show it. But I don't think I can run on it because it is taking another. It might take, and let me see how much time this will take to submit. Estimated time.
No need. Okay. Okay. So they're saying that it's okay. We just run the example and maybe run it on simulator. Simulator should be faster, right?
Yes. Simulator should be fast.
Yeah. We can just run it on simulator, and later they will just try to run it on the actual thing themselves.
Yeah. Right. In fact, most of the things that they submitted should have been processed by now. Like because it's already more than 30 minutes, right? Like if they submitted to some circuit, some computer, it should have been completed so they can see like
Is it
the
done for
details
some
about.
of you? Huh? No, for none of them it is done, it seems.
Okay.
For none of them it's done. Okay. Today somehow it is taking more time, because last time we did it was people were able to do it, right?
Yes, last time it was like within like a couple of minutes, that's it. And but I think today it is maybe I'm not sure why it is, but the last time there were more quantum computers are also available. Today there are only 3 that are available. So maybe that is one of the reasons why there are more jobs on those 3 machines.
So is all of you running on the same machine or different machines? Everybody is running. Which machine? Everybody is Brisbane. Huh? What? Okay. So different machines. Better, because maybe it is possible that something else. Okay. All right. So all right. So then maybe let's go through one more example at least. Yeah. So we'll be delayed like half an hour for lunch. I hope it is fine. Huh? Okay. All right. Okay. Yeah. Let's continue, Naresh. And then later, what will happen is after his example is done, then maybe we will give some other example that you can try at home, okay? And then later, if you have some question, we'll see if we need it. We'll go for another session if needed, okay? But because Naresh will also be traveling starting today, so don't know about that, okay? So, okay, Naresh, continue.
Yeah. Okay. Now let me go to this. I think this file should. Let me shut down. Yeah. Okay. So what should we go over, Rahul? Like super dense coding or the Grover 1/4?
Yeah, maybe 1/4 Grover.
Okay, let's go to 1/4 Grover then. Okay, right. So if all of you can recover Grover's algorithm, let's say,
Okay, Naresh, we have not done Grover's algorithm as yet, but we did that
Okay.
1/4 Grover. Okay, yeah, this one we have done as such. Not
Okay,
Grover's
okay.
algorithm per se. Yeah.
Okay, no worries. So let's say you have like four elements, let's say 0, 0, 1, 1, 0, 1, 1, 0, and then only one of them is marked. So f of 0, 0 is 1 and f of other three is 0. So f of 0, 0 being 1 means 0, 0 is marked like that. And you are given, let's say, query access to, then the number of times you need to invoke that function to output the function value is the problem of Grover's thing. So classically, for classical algorithms, you need like two queries to find out whether 0, 0 or 1 of 4 is marked. But using this quantum algorithm, you can do it in just one query, right? So that is the 4 out of 1 query. 4 out of 1 query algorithm. So okay, let's first again like just invoke the libraries that we need, and let's say this is I'm creating, because I have only two I'm running only on 4 marked elements, right? So there are like 2 bits, 2 qubits. So I'll just invoke to create a Grover circuit on 2 qubits and 2 classical bits. And then now if we just invoke and then I just draw, like you will see nothing, right? So we just created a circuit, empty circuit with 2 classical bits and 2 quantum bits, right? Now, so process is like, let's say we create this. So the goal is, let's say you pick what you want the marked element is. Like for example, here I have picked 1, 1 to be the marked element, and 0, 0, 0, 1 and 1, 0 are not marked. So at the end of it, we should output 1, 1. Okay. So the circuit for is like we first create the circuit which is empty. Then we apply Hadamard, right? We apply Hadamard on everything. Then we create a oracle function. This is the oracle function. So it takes in a circuit and then it gives, like when 1, 1 is marked, it gives us -1. This circuit QC, when act on 1, 1, it gives -1, 1. It acts on 0, 0, it gives 0, 0. It acts on 0, 1, it gives 1, 0. It acts on other 3, it gives like respectively. Okay. Only on 1, 1, it gives -1, 1, which you can see here, right? Like
This is the
if you do
controlled. This is the controlled phase flip. Yeah.
yeah, if you do control phase on 1, 1, you'll get -1, 1, right? Because if you are doing control on the first qubit and on the second qubit is 1, so you will get minus phase added. So 1, 1, it will give -1, 1, right? So okay, so this is the code to actually create this quantum circuit. So let's go on. First, we apply Hadamard gates on the 2 qubits, create a uniform superposition, right? Then we apply the query gate, control Z. This is the oracle query that we have created. On 1, 1, it gives -1, 1. On everything else, it gives 0, 0, it gives 0, 0. 0, 1, it gives 0, 1. 1, 0, it gives 1, 0. 1, 1, it gives -1, 1. Right? Then we do this rotation. Like this is that Hadamard, and then this is that reflection with respect to uniform superposition. Right? So this is the entire algorithm that for one query. If you note, there is only one time we have queried this oracle, right? And everywhere else is not like. So you can see, let's say now we measure the outcome, right? So now let's try to run on the simulator. So I invoke the simulator and then I run. Oh, okay, sorry. So this is what air simulator. Okay, okay. I think I need to invoke I need to do something which is yes. So here, right, before this it showed some error. So let's say I add a cell. Where is this cell? Add right. So here I create this. I just added that. So basically I'm importing this air simulator library. And then I also need to import a transpile. Okay. Let me just import this all. Right. So now let's go here. So we have created this circuit, right? Now let's try to import this air circuit, backend simulator, transpile, circuit. I think it should run now. Yes. So now basically I have so the reason why it showed error is that one, I haven't imported this Qiskit Air and also the transpile library. That's why it showed error recently. So now, like once I imported that, then now you can see the output of our thing is 1-1, right? 1000 times we have run, all the times it is 1-1 because we are running on simulator, right? So this is the circuit that we have prepared. As you can see, this circuit, this is the circuit, right? So first you prepare uniform superposition, then you apply Oracle query, then you apply one reflection. I have used this this things only to tell, like, you know, this is Oracle, this is this, and so on. And then we measured, and then we use the simulator to know the measurement outcome. And then I plotted the histogram of that counts. So all the 1000 times I have gotten 1-1. Okay. So now let's change this. Let's say what happens if the input, if the thing is 0-0 is the marked element, right? So let's say we want to implement.
So in this case, what Naresh did was, Naresh is actually using a slightly different circuit than we saw. Okay. But Naresh, can you just go to the circuit?
Yes.
Yeah. Okay. So the thing is that, you know, remember in our this 1-on-4 thing, we were creating this uniform superposition, and wherever the 1 is there, we were changing the sign. Okay. So in this case, Naresh has changed the sign actually for the 1-1 place. Okay. And then after that, the circuit that he is using is also little different from the circuit we were using after BF. Okay. But that's okay. Let's not worry about it. But the point is, after that, the final he's getting is 1-1. You see, because he changed the sign of 1-1 and he is getting 1-1. Now what he's going to do now, he is going to change the middle one. The middle one is the one that puts the phase. Okay. This is like BF, but BF for the 1 being in the 0, 1, 2, 3, the third location. Now he's going to change it to maybe the second location or the first location, something like that. Okay. And then we can see that the corresponding output will be arrived with probability 1. Okay. And now, but the point is this. The only place the BF is acting is in between the two dotted lines. Okay, the rest is a fixed
Yes.
circuit. He's not going to change the rest of the circuit. The rest of the circuit will remain the fixed. Only between the two dotted line he'll change something. That is the BF part. Okay, because that will mean BF for a different F. Okay, and then he will get the corresponding answer. But from there we can see that he's invoking BF only once. Okay, invoking BF only once. Okay.
Okay. Now let's go and try to change the code for only, let's say when the marked element is instead of 1 1 it is 0 0. Okay. Let's go step by step. We run the same and we'll only change the oracle. Okay. We won't change anything else. Here this oracle. So here the thing that we need to change is this, right? So let's say if it is QC when let's say if it's right QC dot, I think we need to do this. This I think is the QC dot 0 and we do this QC dot X. Now this is the BF when F is like 0 0 is for 0 0 you want to add a phase, right? Like as you can see here for 0 0 the phase will be added. For everything else, the phase won't be added, right? So this is the only difference, right? And now let me just confirm if it is 0 0, right? X 1 1, right? So for only if it is let's say 1 1, then it is 0 0, doesn't add. Okay, okay, got it. So this is the correct BF for marked element is 0 0. Okay, now we did nothing else changes, no changes to anywhere else except that BF change, right? Now you see the circuit has changed, right here, right? So
okay, just hold on to the circuit. You see, now
Yes.
you see what has happened between the first two dotted lines. The circuit has changed. Earlier it was just that controlled phase flip only. Now he has a not and control phase flip, then not. So what is happening now? It is like a control phase flip, but now you are only changing for 0 0 instead of 1 1. Okay, the sign. So now he has changed it only for 0 0. Now you can see that the output will come out to be only 0 0, and rest of the circuit he has not changed. You see, only between the first two dotted lines only he has changed it. And now you will see that the final output will also turn out to be 0 0 with very high probability. Okay, yeah, go ahead.
Now we measure. Now let's say now we run the simulator. You see 0 0 we got with probability 1. 0 0 is the marked element, we got that with probability 1. So this is one thing that I have added for when it was marked. So this is not for this. Okay, yeah. So this is the histogram that I plotted now. You can see here for 0 0 it is showing 1000 times it at 0 0 because we have changed for marked element 0 0, right? That's why 0 0 you get 1000 times.
Okay, if you try to now run this on actual computer, do you think it'll?
Okay, let's try that. Actually, I'm not sure if they will allow, but it's likely that they might say it might not allow me, I think.
Maybe you can cancel some of the previous jobs and try this. Your previous job seems stuck somehow.
Right. Let me see if I can cancel them. Maybe download, cancel.
Okay.
I think I have cancelled. So let's see if this first I invoke this, I get the backend, then I get and then I optimize, get the subviews, and then transpiled. Yes, this gives me the transpiled circuit. Okay, let's see. now
So he's generating the file locally, then he will run it on the machine.
this is the
on the cloud.
transpiled circuit. As you can see,
Yeah.
transpiled circuit is different than the circuit that we ran, right?
Yeah.
Now let me run this circuit on machine, right? On now. Right. So now this is running, and it will give us the job ID, and we can go and check.
Oh, so now it's running on the IBM machine?
It is in the yes. Now it actually ran, it submitted in the queue, like job ID you can see here, it ends with GEG, right?
Yeah.
So now go here.
So you
And now
ran
we
it on
can
your local machine, but it already invoked it in the IBM machine?
Yes,
Ah.
that is correct.
Okay.
So
Okay.
I ran the local machine, I used this token, right?
Yeah.
I use token to tell IBM Quantum website that, oh, I want to run this circuit on your machine, and they submitted in the queue, as there is a queue process, and then they gave, this is your job ID that we are going to process when your queue arrives. So the job ID is the CXJJ7GEG, right? The same thing you can see here,
Yeah.
CXJJ7GEG in the website.
Okay.
And here it says, and here we can see when this is the circuit that I am running, actually the diagram, right?
So is anybody
And,
of you are able to do this? Like run the circuit, get the job ID, and that is actually running on the cloud. Are you able to do that? Huh?
So
No, I mean, are you able to do it now? No? What Naresh just did. You're not able to do it? You need the Jupyter code for that, huh? For simple circuit, you can do it. Get the job ID thing and all that, like, huh? Okay. All right.
okay, I think it just like, I think now it is taking only 10 minutes. They are saying wait time is just 10 minutes. So let's see, like I guess in, so good thing is now you can get the job ID, right? It previously didn't allow me because I had like 3 things that are pending.
Yeah.
So now since I can, now it did allow me to run,
Mm.
and it gave me the job ID which I can check online. Now it is saying it will take 10 minutes to process my request.
Okay.
Right. So I mean, once after 10 minutes we'll get the outcomes, and we can check in here the statistics, we can get plot and then check how many times we get, so on. Right. Yeah.
Maybe you can try the simple circuit, the EPR circuit. Do it on your local and try to run it on the IBM machine. You can do that? You're able to do it? Yeah? Try the simple circuit, the EPR one. Huh? All laptops. All laptops are getting this. Okay, but anyway, I think he will provide you this Jupyter code. So maybe with that you should be able to do it later on, okay? I mean, it would have been nice if you could have done it now so that, you know, you would have known exactly how it happens. But if not also, he will provide you the Jupyter. And this recording will be there. So hopefully you should be able to figure it out later on. So, okay, so this is going to take 10 minutes. So, do you guys want to wait 10 minutes or just head for lunch? Huh? You want to wait, huh? She wants to wait.
Just 9 minutes.
9 minutes. Okay, meanwhile, maybe Naresh, you can also tell them about the superdense coding.
Right. Like this is about Grover now. Now let's say superdense coding. super dense coding is the let's say you covered this both super dense coding and teleportation, right?
Yeah, I
Rahul?
covered both. Yeah.
Okay. In teleportation, like in teleportation, we can communicate any qubit. You can teleport one. You can send one qubit from any qubit from Alice to Bob if they share one EPR pair, right? Like you can send two classical bits, and then your qubit will be sent to the other party. So in super dense coding is the other way around. And now let's try to implement super dense coding protocol. So at the start of it, so basically we send like two classical bits of information to Bob, and let's see. So to perform super dense coding, we need to create EPR state. So let's first go ahead and do that. This is EPR state. Yeah, this is the super dense coding protocol. Let's say the message that we want to transmit from Alice to Bob is like 2 bits, right? We want to send 2 bits of information by using only 1 qubit. That is the goal of super dense coding, right? Let's say we want to send 1 message is 1 or we could have sent it like 0 anything, like any 2 bits we can send. So now let's say the message that we want to send is 1 and I'm creating a super dense coding circuit, empty circuit, so that we can prepare a message. So first, so here we need to prepare our message, right? So first let's create. So this is the code that I have executed to prepare the message. So note initial qubits are initialized in 0, right? So when I apply XX, so it will be like 1, right? So basically you can think of the first 2 qubits I'm using to store classical information. Okay, so based on that qubits, I'll do some operations on these 2 qubits, Q2 and Q3. This is think of Q0 and Q1 as bits that are storing the 2 bits that I want to send from Alice to Bob. Okay, and that's why I've initialized to 0 and then I apply XX because I want to send 1, right? So now and then I create EPR. So and I'm creating EPR state in second and third qubits. 0 and first qubits I'm using to store the message, and 2 and 3 to prepare EPR state. And second qubit is with Alice and third qubit is with Bob. So basically Alice will do something based on 2 bits message and then the Q2. Okay. Now let's say we encode the message according to super dense coding protocol.
Now you can relate it to the circuit actually that we had. Okay. Like yesterday we had one
Let
circuit,
me-
right? So
Yes.
for
So
super dense
you can
coding,
see-
we had one circuit. You can see the operations done was by Alice was controlled phase flip and control not. So
Yes.
what he's now doing, Naresh, sorry, you're doing a Hadamard and a control not.
Control Z and no, this is for EPR pair preparation.
This is just for the EPR pair. Correct. Then you can see there is a controlled knot and a controlled Z, controlled phase flip. He has that one. Okay. All right. Great. Okay. Very good. Yeah. It's the
Right?
same. Okay.
Now we decode message, right? Decode message is same as this one. Like you invert this EPR, like
You see, there was a
use
control
bell
knot
basis
and a
method.
Hadamard. Remember, there was a control knot and a Hadamard in the thing that we had yesterday. It's the same one. Okay. Go ahead.
So this is the super dense coding protocol. Like first you prepared the message that we want to send. You prepared EPR phase in the second phase. In the third blocks, we prepared that encoding circuit. In the fourth block, we prepared the decoding circuit.
So you see, Naresh
Right?
just stated the circuit. Yeah. So you see, the first 2 wires are representing for us what is representing A and B. Okay. Then there was a control knot, control phase on the third wire.
Then the third wire was actually with Alice initially. Then later it went to Bob. Okay, this is the 1 qubit transport. Then Bob is doing this control knot and Hadamard. Okay, and then the output will be there. Now the output will be obtained in the last 2 wires. You see, whatever he had, he prepared 1 1 on the first 2 wires. Now he will get 1 1 on the last 2 wires because he is going to measure the last 2 wires. Go ahead.
Right. Now let's measure this last 2 wires, right? So now you see, like I've measured this last 2 wires, right? Okay. Now let's see let's try to simulate this thing and see. Now you see 1 1, right? 1 1 is what we sent and 1 1 is what we see. Like this is the simulator, like to run the circuit.
Yeah.
On the simulator, right? Sorry. So this is the simulator that I am running, right? Now you see 1000 times I have run and all the times I see 1 1.
So the simulator is running locally or it's also running on the IBM machine?
No, simulator is running locally.
Oh, simulator is running locally. Okay. So that's the advantage of local installation. Then you can run the simulator locally. You don't have to run it on the IBM machine. Otherwise, IBM machine you have to wait.
Yes, IBM machine again you have to wait or like you submit and.
Okay, so that is what it was about the superdense coding. Okay. Now maybe you can change the message.
You can also change 1 1 to 0 0 and then see.
Just try change it, Naresh.
What happened?
Maybe change to 0 1 or something. Change to 0 1.
Let's say like now let's do this for, let's change the message from 0 0 to 0 0, let's say.
No, 0 1. Naresh, change to 0 1.
Okay, 0 1, let's say. And so 0 1 we accordingly message. And here,
now
here
you see he
see
changed the message, right, to 0 1. So earlier he had 1 1, so there was a NOT gate on both the wires. Now he has put only NOT gate on the second wire. Because initially will always be 0 0. You want to change it, you just change the NOT gate accordingly. Okay. Now everything else is the same. You just show the circuit.
Yes.
Show the circuit.
Yeah, this is the end circuit.
The final circuit.
Everything else
is the same, only initial one he has changed. Only AB is changed. Okay, everything is the same. Yeah.
Now let's try to run the simulator. Here you see 0 1.
Now 0 1.
0 1 you see with 1000 times you see 0 1.
Yeah. Okay. So that is the superdense coding.
Okay.
Okay, fantastic. Any questions you guys have? No? Okay, let's see whether the job has run there. On the
That
IBM
is
machine.
correct. So see that.
How much is it left? How much time is left? Is it run already or?
No, it is not yet run. It is saying, let's see what is it saying. It is queue position 123. It was initially saying 10 minutes, right? It is still pending somehow. Yeah, status is still pending, Rahul.
Okay, but is it now saying the time estimate or no? But it is not showing the time estimate now?
Yeah, it is not showing time estimate, as you can see, right, on the website. Initially it gave an estimate of 10 minutes, but somehow it is not showing time estimate now. But it is showing the position is still 119 something.
119.
Yeah.
Still lot of time is there. Okay. Then looks like that their servers are kind of busy or whatever.
Right.
All right then. So doesn't matter. So maybe you can just share these Jupyter files, Naresh, and then
Yes, yes.
they can try to run on their own whenever they get the chance.
Right. Yes, Rahul. Yes, I will share all the files, all the three files, that hello world dot file, and also the files where there are 1:4 marked Grover's algorithm, and also the super dense coding algorithm. I'll share the files so they can run and check for themselves. Yeah.
Okay, great. Yeah, fantastic. And after that, you guys can try to run your own circuits maybe later on. Just a small, maybe Deutsch Jozsa or something like that. You can try to run, or
Yeah.
teleportation or something. You can try to run on your own. Okay. All right,
One
great.
thing is,
Thanks a lot. Yeah.
Yeah.
Go ahead. So, what are you saying?
Yeah. Now you have they have given access to 127 qubits, so you can actually randomly add some gates and try to measure and then check the sample. They are usually random. You can up to run depth 10 circuits also. So you can run many Bunstein-Vazirani algorithms. You can run many algorithms actually.
Yeah. Later.
So, and
yeah.
Best way is to explore Qiskit tutorials which are available online, and then just open them and start running them, and so that you can learn.
Yeah, sure. So, like this kind of a thing he showed, right? I think teleportation I think there are many such things, Jupyter files even available in Qiskit tutorials. If you go, they will have for many tasks like that, right? They will have Jupyter files like that. So you can try those also. Okay? Those will also be there. And then you can try to create your own and also try things like that. Okay? All right. Any questions? No question. Okay, great. So thanks a lot, Naresh. Yeah, it was great. So, yeah. Yes.
So, Mr. Naresh, instead of running a cell by cell, if I have the complete code on a single cell, if I execute from master library to the final execution of simulation output, is it possible?
Come again, can you repeat the question?
Yes. Instead of running cell by cell, if I have a cell complete code up to the simulation backend, if I run in the entire program in a single cell, from the execution I can go to the simulation output directly?
Yes, you can. Jupyter gives such customization. You can run all cells together. You can run until you can create an endpoint and then run till that endpoint. You can do such things.
Okay, great, Naresh. So thanks a lot. Yeah. So you will be traveling, right? So and
Yes.
Yeah. Okay. So, but anyways, if you have any more questions also later, you can just let me know, and then we can try to coordinate and.
Yeah, I can give my email and they can message me if they have any questions. It should be.
Yeah. Even that, Naresh will give email, and then you can also message him. Okay. All right. Great. Thank you, Naresh. Bye then. Bye.
Thank you, Rahul.
Oh, he put the email in the chat. Okay, you can just copy it from there. Okay, thank you. Bye.
Thank you. Bye.
I'll stop the recording now, okay?
Recording stopped.
Okay, we were planning. All right, I'm stopping the Zoom meeting, okay? Okay, so, all right, so now we'll go for lunch. So it's 2 already. Then after lunch, you guys can be back at 3. Is that a possibility? Huh? Because we were planning on a tutorial, 1 hour. Or we can shift it a little bit, 3:30 to 4:30, like that we can do. 3:30 gives more time for lunch. Better? Yes? $3:30. Let's do 3:30 to 4:30. Okay? Come back for tutorial. All right.
Yeah, related to the things that we have done before. So just a refresher, as we said that the bell states, these are the 4 bell states here, right? There are 4 orthonormal states between themselves. This is the teleportation protocol. It's just the circuit for that, okay? Okay, here's a question about teleportation, but maybe we'll get to it later, okay? Let's get to this question. Remember we said that we try to do this in tutorial, right? This formula about the Hadamard H tensor n, okay? Yes, so we need volunteer, please. I would encourage other people who have not come before to come as well. But anyway, you can come. Is there anybody else who wants to come? Who has not come? They will get preference. If you have not come before, you will get preference. Okay? All right. Okay, very good, very good, very good. So, see what he has written there, the Hadamard transformation on x, where x is 1 bit, okay. So, the special case of n equal to 1, okay. The special case of n equal to 1, he has written, maybe you can even write it in this form. Okay, fantastic. So maybe you can take the mic and explain this one. So you see he has written the special case of n equal to 1 in this form, okay? Yeah.
Okay, until here the idea is that we take this particular case and generalize it for any x. Anyway, -1 is coming when this is 1. So like we have seen in many scenarios yesterday, -1 raised to x is a good way to achieve that. And this step sir told, so I just took a leap of faith, but I should figure out now what is happening exactly. This is anyway 1 qubit is there, so this is all possible one size subsets, which is 0 and 1. And okay, here we have h of x. Okay, so if this is 0, this will be, when this is 0, this is minus 1 power 0, so it will be plus only, which is what we desire. And if this is h of 1, then we expect minus here, and for that
no, you see h of 0, h of ket 0, you consider both y equal to 0 and y equal to 1.
h of ket, consider both y equal to 0 and y equal to 1.
Yes.
Shall I write it down?
No, just
okay,
explain.
just tell.
Just
For
explain.
0 it was fine. For 1 what happens? Okay.
No, x is 1, x is 0, y is 1.
Okay. X is 0.
Y is 1.
And suppose y is 1. Okay. So this dot product will again be 0.
Yes.
So we will have plus only here.
Correct.
Okay.
Do you see that?
Cool. Yeah.
Yes.
And
now x is 1.
So now if x is 1 and y has two possibilities, 0 and y is 1. Suppose we take x is 1 and y is 0. Then since x is 1, we'll have minus 1 power 1 dot 0 for y equal to 0. So this will become plus of 0, which is what we desire. And when x is 1 and y is also 1, that is, we are actually finding h of 1. That is a summary. So here we expect a minus and we do get a minus. That is, x dot y will be 1 dot 1 1. So we'll have minus 1 power 1 y. So it will be minus.
Clear?
Yeah.
Yes? Any questions? If you have any questions, you can ask. So that is a compact way of writing. What he has written here is a compact way of writing h of x. Agreed?
Yeah.
H of ket x. Very good. That is for n equal to 1. Now let us generalize for general n.
Yeah, general n. For
this, okay.
Actually, for a little clarity, I would like to look into 2 qubit case, and then leap would be easier, I am feeling. So h2 on x, but in this case x has 2 qubits, x1 and x, I mean
Okay.
H
Sure.
has 2 bits,
Yes.
x1 and x2. Then the possibilities are, actually if we see what happens by enumerating all cases, we'll have root 2 power 2, and here we'll have 0 0 and plus, okay, we must make a small change here, but I am just taking it. Okay, to help this, let us see what happens when we have just 0. Then we need not worry about sign, we can happily write all the cases.
Okay, actually, what I would suggest is, see, since you have already written this compact form, right?
Okay.
Okay. Why don't you
generalize that
use
one.
this compact
Okay.
form?
Okay.
Maybe it's better.
Okay. We have 2 header map, 1 for each bit here, x1, x2. Then of course we'll have 1 by root 2, so it will be 1 by root 2 square. Then here we will have all possible subsets of size, 2 to element subsets, and Here we have minus 1 power x dot y. If we use this, it's like directly we are writing.
No, 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 no. That is what you have to prove.
Huh.
I'm saying you have shown
one.
this already.
Huh.
Maybe you can try to just use this to show this.
Okay.
You see what I'm saying?
Okay. Okay. Using that, we can consider this as h of x1, h of x2.
Yes.
One way to go about it.
Yes.
Okay.
Correct. See this?
Now, individually, we know, we have seen in the previous step.
See this thing? Right?
Okay.
Now go ahead.
Okay. Power, here it will be x1 dot y times y plus everything same. Not plus, sorry. It is actually tensor product. It
Yes.
will be tensor product.
Yes.
1 by root 2.
No, then you should put a bracket. You see, whenever you have a summation like this, you should always put a bracket.
Correct. x2 dot y in this case.
No. See, as we said, whenever we have two different summations, we should never use the same
correct
variable.
So we shall call this as now.
You can call this y1, call this y1,
and this will be y2.
y2.
Correct.
Correct?
Yes. Anywhere else? Yeah, here. y2.
I think it's getting very cluttered here. Maybe you can write it here.
Here.
Erase all this and you can write it here.
Now time to bring both of them together.
No, you write this thing again because people cannot see this one.
Okay. Here.
Okay.
Okay.
You can keep the mic down, you can write it first, then explain. Yes. Now you can try to combine them. Yeah, you can erase that. Huh? You want to go? Yes, very good, very good. Very good. So now is it looking like this now? For n equal to 2, is it looking like this? X dot y, what is x dot y? Write x dot y. Write the x dot y for 2, x1, x2, y1, y2, right? No, don't write like this because people cannot see. If you write it like this, you write it here in the space here, here. What was the definition of the x dot y? And mod 2. Correct? You got it? Yes, very good, very good. So this expression is exactly this expression for n equal to 2. Okay, maybe you can now take the mic and explain.
Okay, so one qubit case with Hadamard, one Hadamard gate we had seen. Now for x, which is of the form say 0 0 0 1 1 0 1 1, for all these possibilities let us consider say it is containing 2 bits x1 and x2 in general. Then on total we just call it as x. So for that we are applying 2 Hadamard gates, one for x1 and the other for x2. That in compact form we are writing it as h, this notation x. And when we do that, we are applying for both these both these bits x1 and x2. So first for x1 we are using the result that we had written before.
Is that one clear? The board, is it clear on the video? Is the board clear on the video? Clear? Ah, okay. Maybe you, yeah.
Okay. And maybe I'll pull it front, is it?
No, it's okay.
Okay. And similar thing for second qubit as well. So one is for x1, the other is for x2 with tensor product in between. Now we are just writing them together, one summation inside the other one, and yeah, here just writing together, and 1 by root 2, 1 by root 2, we have 1 by root of 2 square, and in each case y1, yeah, this is same, not much different here, just writing together. But in next step we are bringing things together, that we have this minus 1 power x1 y1 and minus 1 power x2 y2. Bases being same, we can just add the powers, but since we are in binary terms, it will be parity. That is the reason it is parity.
Yeah. Remember we had this formula, minus 1 to the A times minus 1 to the B is minus 1 to the A parity B.
Correct. Yeah.
Which is another way you can write A plus B mod 2.
Yeah. Okay. Now this term we can see that this is nothing but the dot product of the x and y, where x is, as we had seen before, x1, x2, the 2 bits, and y is also y1 and y2. Here one we have. So on the whole we have x dot y, which gives us the required result. So next we just need to replace 2 by n and it will be generalized expression.
Clear? Clear? So he has shown it for 2, but we can similarly proceed. Okay. Great. Thank you.
Thank you, sir.
Okay, now let's look at this one. Remember, some people were talking about the show that this is not possible to construct a general quantum cloner with unitaries. That is, no unitary can take phi and all zeros to 2 copies of phi. Okay, this is the cloner, right? Copy quantum phi to phi and all zeros to 2 copies of phi for all phi. This is not possible. There cannot be a unitary which can do this. We want to show this. Okay. All right. So we need a volunteer for this. Yes. Okay. Yes, please come. Maybe you can write little bigger, huh? Because I think people from back cannot see. You can try to move forward a little bit. You can also use that space, the other one. Write a little bigger, huh? Too small. Can you guys see? Okay. Can you please explain?
So the question is like, it's saying that there is a unitary operator which we apply on a quantum state, then it will clone the quantum state. So we need to prove that it is not possible because of the no cloning theorem. So suppose we are proving by contradiction. Suppose there exists a unitary operator U that can clone a quantum state, that can clone a given arbitrary quantum state, anything. So let's take the quantum state as alpha 0 and beta 1, and then by our assumption, because this is a proof by contradiction, so we are assuming that this unitary operator can clone the quantum state. So I'm just taking here 0, you can take any get 1 also. So unitary operator applied to this arbitrary quantum state, it should clone. So I am supposing that this equation is 0, and from this we can say that unitary operation psi ket 0. So we took that arbitrary quantum state as alpha 0 plus beta ket 1. So by applying this 0 to this ket 0 0 and ket 1 0, we get this, and unitary operator we are taking it inside. So this is equation 1, and then from our assumption that it can clone, we can write like this, ket psi and ket psi. So we know that ket psi is alpha ket 0 plus beta ket 1. Again I am writing here both. So we are multiplying this alpha square ket 0 0 alpha beta ket 0 1 ket 1 0 and plus beta square ket 1 1. Suppose that I am saying this is equation 2, but on LHS we have same terms, but on RHS it is not same. So equation 1 is not equal to equation 2. So by contradiction we can say that this there is no such unitary operation that can clone a given arbitrary quantum state.
Okay.
And this one is which we have taken assumption which can clone.
Yeah.
So by multiplying this we got this one. So but this is not equal to this one. So we can say that there is no such unitary operation.
No. How do you know that this is not the same as this one? This is the U here, right?
Unitary operation is that.
There is a U here, no? There is no U there. Right? Yeah, we can do that. You see what I'm saying? There is a U here, no? You haven't applied the U here.
U should be set 0, 0, beta 1.
U
should go to 0, 0. When applying to 0, 0, it will go to
0, 0, and here this will go to?
This will go to 1, 1,
1, 1. Ah, then write it here. Write it here. Ah, that's better. Ah, now you write it. Correct? Ah. Right. Now it is not going to be the same. Why? If alpha and beta are non-zero, then it will not be like that. Correct?
Correct.
See? You saw, follow what he wrote? Maybe you explain one more time. Just slowly you explain one more time, the whole thing.
So basically this proof is by contradiction. So I am assuming that there is unitary operation that can clone a quantum state. So I am taking my quantum state as alpha ket 0 plus beta ket 1. So by our assumption that it can clone, we can say that it is cloning the same arbitrary state ket psi as ket psi by applying this unitary operation to our original state. So we apply this unitary gate to ket 0. So we get unitary state is alpha ket 0 plus beta ket 1. So by taking this ket 0 into inside, we get ket 0 0 and ket 1 0. So by applying this unitary, we get this alpha ket 0 0 plus beta ket 1 1. Say our assumption like this is equation 1, and then also from our assumption that it is cloning the arbitrary state. So ket psi psi, we are writing it on RHS. So ket psi is alpha ket 0 plus beta ket 1. By multiplying this, we get alpha square, alpha beta and beta square. So but this is not equal to this first equation. So we can say that there is no such unitary operations that will clone a given quantum state.
The thing is that 2 will not be equal to 1. You can choose some value of alpha beta so that 2 is not the same as 1, right? In which case it is a contradiction. Okay. Ah, yes. U00 goes to 00 and U10 goes to 11. Okay. That is what it is. Okay, very good. Now B. So this shows that there is no U which can copy quantum states. Okay. Yes. Yes. Yes, that is also, yeah, but it looks like a bell pair. So yeah. Yeah, for example, yeah, you can say that if you choose, for example, alpha and beta to be 1 over square root 2, that's exactly the EPR pair, and it cannot be written as a tensor, so it's not possible. That's another way. Yeah. No, no, many zeros is simply to match the number of zeros in number of qubits in phi. If phi is a n qubit state, it is a n zeros. That's all. What he has taken is a case of 1 qubit. Okay. Yeah. Part B. Part B. So this part A shows that we cannot copy quantum states. This part B shows that we cannot delete quantum states. So that is, there is no 1 qubit unitary U that maps psi to 0 for every 1 qubit state psi. We want to show that this is the case. How can we show that? Yes? Anybody? Yes, exactly. Exactly. So it won't be invertible. But just how can you show it formally? No, what you said is perfectly alright. But just to show it formally. See, what he said was that if every state is mapped to 0, it is like a many to one, right? Mapping. Then it is not invertible. For invertibility, you should have one kind of 1 to 1. Agreed? Any lossy map is not invertible. So therefore, this should not happen. But just to argue formally. Anybody? Just come, doesn't matter. Just come. We'll do it together. Okay. Yes? Anyone? Just come. Doesn't matter. Anyone? Yes? Okay, maybe. Would you like to come? Just come. Behind you. Yes. We'll do it together, don't worry. Huh? No? How about you? You want to come? Yeah. Just come, doesn't matter. Huh? You want to come? No volunteer. Very easy, I tell you this one, very easy. You can come, I know, but the only thing is, maybe people who have not come before. You have come before? You have come before? Yes or no? You have come? Come, come. Okay. Yeah. So first what we will do is we will show that unity transformations are inner product preserving. Okay, what we will show inner product preserving means that suppose you have a state psi, okay, psi 1 is u times psi, psi 2 sorry phi 1 is u times phi, okay. We want to argue that the inner product of psi 1 with phi 1 is the same as inner product of psi with phi, okay. You see this? This is called as inner product preserving, inner product preserving, okay. Now, okay, let's try to first show this, that unity transformations are inner product preserving, okay. Exactly, dagger. Yes, very good, very good. No, you write it as the psi 1 dagger. Just write what is ket psi 1. Ket psi 1, write ket psi 1. No, what is ket psi 1? You just write there. U psi, put the whole thing dagger. Agreed? Yes? Now write it. What is A, B dagger? Remember the formula? B dagger, A dagger. B. Very good. Yes. Yes, very good. Correct? Identity times phi is just phi. Correct. Okay. Now just take the mic and explain.
So this can be written as like this psi can be written as this dagger, and then we have replaced this with the whatever value we have, unity transformation on.
No, you first explain what you are trying to show. What you are trying to show, you first explain that.
So we are trying to show that the inner product is preserving. Means if we have this psi 1 and phi 1, so bracket psi 1 phi 1 is equal to same. This thing we have to show.
Yes.
And this is equal to unity transformation over psi, and this is equal to the unity transformation over phi.
Yes.
So if we perform this, it means dagger of psi dagger, and then phi.
Psi 1.
Sorry. This is psi 1. So psi 1 is basically psi dagger.
No, psi 1 dagger.
Psi 1 dagger, and psi 1 dagger is psi 1 is basically unity transformation over psi. So we have replaced this value with this, and dagger sign is remaining as it is. And then this ket phi is written as
ket phi 1.
Ket phi 1 is written as unity transformation over cat phi.
Yes.
And then the formula is AB dagger is equal to B dagger A dagger.
Correct.
So that we have applied the formula, so dagger over phi, and then unity transformation dagger. And as it is a unity transformation, so U dagger U or U dagger is equal to identity.
Correct.
And then we got only this.
Correct.
And this is same as this.
Clear? Any questions? So a unity transformation is inner product preserving, right? Now, in particular, it means that the L2 norm of psi 1, so it is also norm preserving, L2 norm preserving. That is, L2 norm of psi 1 is the same as L2 norm of psi. Can you show that also? L2 norm of psi 1 is the same as L2 norm of psi.
L2 norm of psi 1
L2 norm of psi 1 is the same as L2 norm of psi. Or L2 norm square of psi 1 is the same as L2 norm square of psi. It's the same thing. Can you show that? It is inner product preserving and hence L2 norm preserving. So, can you show that also? Just do it. No, L2 norm square of psi 1, right? L2 norm square, yes, very good, of psi 1 is equal to, what is the formula? It is the inner product of psi 1 with itself. Inner product of psi 1 inner product of psi 1 with itself. Okay, this is the formula for L2 norm square. Okay, now this is the same as, write it by our what we have shown before. It is the same as L2 norm is the inner product of it is the same as inner product of psi and psi. Remember, just write it is the same as inner product of psi and psi. Why? You see that why? Using just put phi 1 equal to also psi 1. Here, remember, no, here, in this on the left hand side, put phi 1 equal to psi 1.
Here.
What are you going to get? Psi 1. Oh, no, either also 1. Yes. Equal to psi with psi. You're going to get it right? That is what you're getting here. Agreed? So that means that is the same, right? That is equal to final equal to L2 norm square of psi. Agreed? So that means it is L2 norm preserving also unitary transformations. Agreed? Very good. Now you erase all this. Maybe erase the right hand side fully. Erase the right hand side. Okay. Now let us say that there is a unitary transformation U which takes psi 1 to 0 equal to 0, right? No, equal to get 0. Okay, now U, right, U psi 2 also equal to 0, correct? So assume that there is a unitary transformation which is taking every state to 0. So it is taking psi 1 to 0, it is taking psi 2 to 0 also, where psi 2 is different from psi 1. Now let us use the fact that it is inner product preserving. Okay, use this formula now. Use this formula. Inner product preserving. Here. Yes, that formula. Inner product preserving. What will you get? use the fact that it is inner product preserving. So what will you get? Yes, equal to yes, very good. Yes, get it? Using that formula, this is what we are going to get, inner product preserving. Now what is the what is this inner product of 0 with itself? Huh? 1, right there, 1, correct. So what does it mean? Inner product of psi 1 and psi 2 is 1. That is not possible, no? That should be true for every psi 1, psi 2. How can every psi 1, psi 2 inner product be 1? In particular, suppose psi 1 and psi 2 are orthogonal. Inner product is what? 0. Then how we can be 1? So that is a contradiction. You see this? If every psi goes to 0, that means u psi 1 also go to 0, u psi 2 also go to 0. Now unitary is inner product preserving. That means inner product of psi 1, psi 2 must be inner product of 0 with itself, which is 1. Then for every psi 1, psi 2 inner product should be 1. Not possible. Right? So contradiction. Got it?
So basically, like we are saying, this is 1. So one counted is that if they are orthogonal, then that is 0.
Yes.
So we can simply say that
It's not possible. Exactly. Correct? Okay, thank you very much. All right. Every unitary has the property that it is inner product preserving, and hence L2 norm preserving. Okay. Remember, we had argued before that stochastic matrices are L1 norm preserving. Now here they are L2 norm preserving. Okay. Any questions? Any questions? Okay, so tomorrow is off. Tomorrow maybe there is some excursion or something, and then Sunday we have class. I think Professor Subba Reddy will take a class at 11, or what time I don't know, he will inform, but let's say by default 11. There is a class on Sunday. Okay. So Sunday you guys are around here, right? Okay, then we may also have a tutorial in the afternoon, and then Monday on will resume as before. Okay. All right, great, thank you.